This says initially the switch in figure 2661 is in position A and capacitors C2 and C3 are uncharged. Then the switch is flipped to position B. Afterward, what are the charge on and the potential difference across each capacitor? So what we have is a 100-volt power supply. So I will label this as Psi, and that EMF is 100 volts. And this initially is attached to a capacitor. I'm going to just draw it like this. So this capacitor has capacitance of C1, and we have a switch that can go back and forth between two parts of this circuit. So the second part of this circuit has two additional capacitors. So we will call this C2, we will call this C3. And what I'm going to do, because I like expressing things as multiples of other things, I'm going to do that. So I see capacitor 1 is 15 microfarads. Capacitor 2 is 20 microfarads, which would be, let's see, so we will say 20 over 15 C, and got to do simple math in my head on the spot, cancel the 5. So this is going to be 4/3 C if I did my math correctly. And then C3 is equal to 2C. And the reason why I'm expressing those as multiples of each other is often it makes the algebra simpler. And that's just something I like to do with circuits, because oftentimes I see things will cancel out pretty nicely. Now, what we have is, we'll say initially each capacitor is uncharged because the battery isn't connected to anything. And we throw the switch, and when we first throw the switch, it connects capacitor C1 to the battery. Now, we assume that after a period of time, capacitor C1 becomes fully charged. And I'm trying not to say too much because I want you to offer me some information. But after capacitor C1 is fully charged, we then flip the switch, and now capacitor C1 is attached in series to capacitors C2 and C3. And the question is, find the charge on and potential difference across each capacitor. So I'll just say the charge on capacitor 1, charge on capacitor 2, charge on capacitor 3. And we also have to find the potential difference across capacitor 1, across capacitor 2, and across capacitor 3. Let's go ahead and try and walk through this together. So we have this circuit. I'm going to go back to when we initially charge the capacitor, because capacitor C1, because that's going to give us a lot of good information. Let me go ahead and create some nodes here. So I guess the book is using capital A and capital B. I don't know if I like their notation. I'm just going to call this A, and I'll call this one B, and I'll call this one C. And actually, let's call wherever the top of the switch is point B. Okay, so just to practice a couple of things, I know that in this circuit right here, we have capacitor C1, and if this capacitor is fully charged, it's going to have an amount of charge on it, Q1. Now, because we want to look at things after we flip the switch, instead of calling this Q1, I'm going to call it Q1 0 or Q01 to correspond to the initial charge of our capacitor 1 when it's fully charged. Now, we ultimately need to know the charge on each of our capacitors after we throw the switch. So since we throw the switch, I know that whatever charge is on capacitor 1 is going to have to redistribute to the other two capacitors. So let's find this initial amount on capacitor 1, which will very likely change once we throw the switch. But at least it'll be additional information we can use. So let's also call the initial potential difference on capacitor 1 when it's fully charged. I'll call it delta V naught 1. And just by using Kirchhoff's loop law, I know the voltage from A to B plus the voltage from B back to A must sum to 0. So what this means is that the EMF of the battery, it's the voltage from A to B, plus the voltage from B to A must be equal to 0. The voltage from B to A is equal to minus the EMF of the battery. And that voltage from B to A is just the voltage across our capacitor when it is attached to our circuit. So that's 100 volts. Well, we can use that to find that initial charge on our capacitor because we know the relationship of Valley College is quaint. So this is the initial charge on the capacitor is equal to that initial potential difference times the capacitance. So this, I'm going to store it for later. We know the initial potential difference. That initial potential difference is 100 volts. And since this is Valley College's quaint, we're going to end up taking the magnitude of that EMF because this formula relating potential difference, capacitance, and charge corresponds to the magnitude of those quantities. So I'll just go ahead and write this as Psi times the capacitance of capacitor 1. Okay, so we now know what the charge on capacitor 1 is before we throw the switch. I'm going to just recopy this to the next page. Okay, so we now throw the switch. And when we throw the switch, our point B moves. So here's the thing now. Capacitor 1, when we initially throw the switch, is fully charged. It is the source of the charge that gets redistributed for the rest of the circuit. Capacitors C2 and C3 are uncharged. So how we should proceed on this is to treat capacitors 2 and 3 as if they're a single capacitor, a single equivalent capacitor. And so I am going to just redraw this circuit with this as capacitor 1. And in this redrawn circuit, I have capacitors C2 and C3 represented as an equivalent capacitor. This equivalent capacitor has an equivalent charge, and the charge on capacitor C1 is going to change. So I'll just call that Q1 now instead of Q01. And the potential difference across capacitor 1 will change as well because the charge will change. So this is, by doing it like this, we are trying to maximize the information we have. And all we can really know at this point is that initial amount of charge gets redistributed between our equivalent capacitor that is initially uncharged and our fully charged capacitor. And after a very short amount of time, our fully charged capacitor then shares some of its charge with with the equivalent capacitor 2 and 3. So the total amount of charge that we have, that we started with, Q01, has to be redistributed between capacitor 1 and our equivalent capacitor 2 and 3. Now, we should know one thing that, here's a tricky thing about this circuit. Are these capacitors in series? Are they in parallel? It's kind of ambiguous because it's just a single loop. It's both in series and in parallel, right? Because they both share 2 points in common and they both go one right after the other. So it's a little bit difficult to say, if you use the rules, capacitor C1 should have the same charge as capacitor C2, as capacitor C3, doesn't work quite the same in this context because it's just this single loop where everything is kind of connected. So we have to take a little bit of a step back, which is what we're doing with this first expression with the total charge. Okay, so what do you think we could do with this right here? Well, let's start. Let's write some other information that we might know. You know, if I call this point A and I call this point B, then capacitor 1 is in parallel. You could consider it to be in parallel with capacitors 2 and 3. So we could say that the potential difference across capacitor 1 has to be equal to the potential difference across the equivalent capacitor of 2 and 3. Now, remember from Valley College's quaint, the potential difference across capacitor 1 is the charge on capacitor 1 over capacitor 1's capacitance. And that has to be equal to the ratio of the charge on our equivalent capacitor over the equivalent capacitance. Excuse me. So if we look at this expression right here, we don't know Q1, but we do have a relationship that relates Q1 and the charge on the equivalent capacitor, Q2 and Q3. Here I have two equations. I see I have three unknowns. My unknowns are Q1, Q23, and C23. So let's go ahead and find that equivalent capacitance, C23, because I think we know how to do it. Remember that equivalent capacitor, C23, comes from the equivalent, or comes from the series connection of capacitors 2 and 3. And when we do that series connection of capacitors 2 and 3 to get our equivalent capacitance, we know that the equivalent capacitance of capacitors in series is equal to the reciprocal of the sum of the reciprocals of the individual capacitors. So what that means is this. I'm just going to do it like this. C1 over C, and in fact, let's just scroll down a little bit. So 1 over the equivalent capacitance is equal to 1 over C2 plus 1 over C3. This means that if we get the common denominator, this would be C2 plus C3 over C2, 3. And then when we take the reciprocal of this to get the equivalent capacitance, we get C2, C3 over C2 plus C3. And I'm going to go ahead and use my proportions that I set up here. So I know C2 is 4/3 C3 and C3 is 2C. So, oh, and this is the product in the numerator, C2, C3 in the numerator. So this is 4/3 C times 2C over 4/3 C plus 2C. Well, there's a C that cancels in the numerator and denominator. I am going to go ahead and multiply the numerator and denominator by 3/3. And that 3/3, this 3 cancels with this 3 in the numerator. So in the numerator, I have 8C. And in the denominator, I have 4 plus 6 because this distributes there and this cancels with this one over here. So this becomes 8/10 C, which is the same thing as 4/5 C. So we now found the equivalent capacitance for capacitors 2 and 3, if I didn't make a dumb algebraic mistake. So the equivalent capacitance should be 4/5 of the capacitance of capacitor 1. So here is our next equation we can use. And now we have 3 equations. Equation 1, which has Q1 and Q2, 3. Equation 2, which has Q1 and Q2, 3 and C2, 3. And equation 3. 3 equations, 3 unknowns. We found for one of those unknowns. We should be able to find the charge on Q1 if we want, or find the charge on Q2, 3 if we want. Either way. So any questions on how I'm proceeding here? And I know it's over time, but we'll finish this problem. Go ahead.
Why did the equation 2 use the parallel instead of in series? Because you just set up between A and B and they split? Or
well, because voltage is path independent. So here, if we are saying that the voltage, this is the voltage from A to B. The voltage from A to B will always be the same regardless of which path you go in. So here, this is the voltage from A to B going across capacitor 1. This is the voltage from A to B going across capacitor 2. They're the same. And you could look at it like that, or if you just wanted to use Kirchhoff's loop law, for example, if we want to just go in a complete loop from A to A, the voltage from A to A, and this would be the way of looking at it in series, is the voltage from A to B plus the voltage from B to A, that has to be equal to 0. So the voltage from A to B is, and remember, this is going to be minus plus, minus plus. The voltage from A to B is just the voltage across capacitor 1. The voltage from B to A is the voltage across capacitors 2, 3. And notice we get that the voltages are equal in magnitude, but opposite in orientation. And that makes sense. So if we're looking at the magnitude of these voltages, we end up with what I wrote over here. So whether you look at it in series or in parallel, you get the same expression for equation 2. Is that okay, Joseph?
Yes, thank you.
You're welcome. Okay, so I guess I will let's solve for the equivalent charge on 2, 3 in terms of Q1. So I'm going to take equation 2, and I'm going to solve Q Q23 in terms of Q1. Okay, and by doing that, I'm just reducing the unknowns we have. I'll call this equation 4. And now that I have equation 4, I'm going to put equation 4 into equation 1. Remember, equation 1 said that our initial charge on capacitor 1 is equal to the new charge on capacitor 1 plus the charge on our equivalent capacitor combination. So this is Q01. We're going to take we have Q1, which is what I'm looking for. We're going to take this expression for Q23 and plug it in. So this is plus C23 over C1 Q1. And this means that we could factor out the Q1 from both those terms. And when we do that, we get an expression for the charge on capacitor 1 being equal to the initial charge on capacitor 1 over 1 plus the ratio of the capacitances of our equivalent capacitor and our capacitor 1. So when I do this, we said earlier that the initial charge on capacitor 1 was equal to the initial potential difference on capacitor 1 times its capacitance. And we called that just the EMF times C. So this means the charge on capacitor 1 is the EMF times C divided by 1 plus, well, remember the equivalent capacitance of capacitors 2 and 3 we said was 4/5 C, and then C1 is just C. So this is 4/5 C divided by C. The C's cancel. And we have Q1 is equal to the EMF C 1 plus 4/5. So 9/5. 9. Well, maybe I shouldn't do so much in my head. So that should be 9/5. And now we have an expression for the charge on Q1. The charge on Q1 is 5/9 of the initial charge on Q1. So ultimately, we need to find the charge on Q2 and Q3. And remember, Q2 and Q3 come from our equivalent series connection between capacitors 2 and capacitor 3. And we know that because these capacitors are in series, the equivalent capacitance of 2,3 is equal to the equivalent charge on the equivalent capacitor 2,3 is equivalent to the charge on each of the capacitors that make up that equivalent capacitor because they are in series. And we have an expression for Q23. Q23 we said was equal to this quantity right here. And I'm gonna just copy and paste that. So it is equal to this quantity right there. And we know that C23 was equal to 4/5 C over C. That is this ratio right here times Q1, which is 5/9 Capacitor C. So this 5 cancels with this 5. This C cancels with this C. And what we end up with is our equivalent charge looks to be 4/9 the EMF of our power supply times C. And this happens to be equal to the charge on Q2 and the charge on Q3 because they are in series with each other. Oh, and look at this. Oh, this makes total sense, right? Because when you add Q1 to Q23, notice how we get 9/9, or the product of the EMF and the capacitance of capacitor 1. So we've now found the charge on each of our capacitors. And let's take a step back and recap, because there is a lot here. But if you could take a step back and recap, we could look at the main steps we took. You know, we first charged the capacitor. So we'll say we first found the initial charge on our capacitor. We threw the switch, but in throwing the switch, and this one part is what I think makes this question challenging. When you first throw the switch, that capacitor 1 is the source of all of the charge. That capacitor 1 is the source of the potential difference. Because of that, we chose to treat capacitors 2 and 3 as if they're other components in a circuit. Instead of creating one giant equivalent capacitor with all 3 capacitors, in fact, we couldn't really do that initially, because in order to create that equivalent capacitor, we had to assume we have to know what the voltage is in our circuit. And the only way we knew what the voltage was in our circuit was by knowing that initial voltage that capacitor 1 was charged with. So we used that initial voltage that capacitor 1 was charged with, and we used that to put capacitors 2 and 3 in an equivalent capacitor, C23. So we made the problem a little bit simpler because it's easier for us to find out information for this circuit than, because it's an equivalent circuit and we have information about the equivalent circuit. Once we found our equivalent capacitance, we then used that and our equations for voltages. We used that to determine one of the charges. I chose to determine charge Q1 first. We could have chosen to determine 2 and 3. It just depended on how we wanted to express our unknowns. And that's essentially what we did so far. Any questions on this? Okay, well, the last part, finding the voltages, goes very quickly because we are just going to use the relationship of Valley College's quaint rearranged. So the voltage across each of our capacitors, the potential difference, is just the ratio of its charge to its capacitance. So if we want to find the potential difference on capacitor 1, it's just the charge on capacitor 1 over capacitor 1's capacitance. Well, the charge on capacitor 1 is 5/9 times the product of the EMF over its capacitance divided by its capacitance. So the potential difference across capacitor 1 is just 5/9 the EMF of our original power source, the battery. To find the potential difference across capacitor 2, that's just the ratio of the charge across capacitor 2 over capacitor 2's capacitance. Well, the charge on capacitor 2 is 4/9 times the product of the EMF over the capacitance of capacitor 1. And capacitor 2, I think we said was 4/9, I think, or is it 4/5? Let me look at it. Oh, 4/3. So the capacitance of capacitor 2 is 4/3 the capacitance of capacitor 1. So the capacitances cancel, the 4s cancel. We end up with 3/9, and 3/9 ends up being 1/3 the EMF of our original power supply. So we've now found the potential difference across capacitor 1, the potential difference across capacitor 2, and finally, the potential difference across capacitor 3 is just the ratio of its charge over its capacitance. Well, its charge is the same charge as the charge on capacitor 2. Its capacitance is twice the capacitance of capacitor 1. So those cancels. This 2 cancels with one of those. So we have 2/9 times the EMF of our charging power supply. So we've now found each potential difference and the charge on each of our capacitors.